my name is Angela Chu, and I'm a solution architect at Databricks, and I'm a member of the streaming subject matter expert group there. And I'm here to talk to you guys today about arbitrary stateful operations. This is flatMapGroupsWithState and applying pandas with state. And we are just going to take the fear out of using those two functions. So before I get started, I just wanted to, by a show of hands, in you guys' careers, how many of you just the data is always in the exact form you need, and those business requirements totally straightforward, and you're golden, just no problems at all? Yeah. If anybody had raised their hands, I would have asked if they were hiring. Because at the end of the day, we know that just, as one of my customers likes to say, data happens. That data is not in what the format you need, and those business requirements are never straightforward. When you've got something that does not fit into the standard set of tools, what you got in your toolbox, that is where you need arbitrary stateful operations, and that's why I'm talking to you guys about it today. So here's what we're going to cover. First, we're briefly going to just say what are arbitrary stateful operations for the folks in the room that don't know. And then I'm going to give you a summary of a real-world use case that I did encounter as part of my job with a customer. I'm going to show you briefly how to think about flatMapGroupsWithState and applying pandas with state logic. When you are trying to organize it, how are you supposed to think about what you're writing? Then the majority of the talk is going to be about breaking down the logic into its components. There are 4 components that you need to consider, really just 4, when you are going to implement flatMapGroupsWithState or applying pandas with state. During that section of the presentation, I am going to be stepping through code. I'm going to be explaining what each of these categories is and examples of both Scala and the new Python code for these functions. Once we go through that and build a complete example for each, I'm going to show you how it integrates into your Spark structured stream. Then we'll just talk about a few best practices and additional things to consider. So all right, let's get started. So what are arbitrary stateful operations? Well, really what you want to do is substitute the word arbitrary with custom. So how many of you guys here actually use Spark structured streaming or are familiar with Spark structured streaming? Yeah, that's good. All right. So for the few that aren't, Spark structured streaming has a lot of built-in stateful operators, like windowed aggregators and deduplication, things like that, where with the use of watermarks, the system is going to automatically store and manage data in between microbatches. When structured streaming is pulling in something from the source and then spitting it out at the other end, if it needs to compute something over the span of 10 minutes, it may have pulled in 50 microbatches during that time span. It has to save data in between microbatches, and the data it's saving is called state. Now, there are use cases that are going to require more complex logic than these built-in functions. In that case, users need to be able to define their own. How long do they want to keep certain records in state? When do they want to output computations? When do they want to output no computations but continue to maintain records? This is what arbitrary stateful operations is for, to allow you to customize this functionality in Spark structured streaming. We are going to try the clicker. Here we go. Nope, and it delayed. All right. So this is a real-world use case that I encountered. A customer had a need. They are tracking transactions from users. So when a transaction is received for a user, they need to be able to calculate the number of transactions that have been received for that user within the last 5 minutes of the transaction that they have in hand. When they do this computation, they need to write the result to a downstream table. Only the current count for each user needs to be maintained. So if no transactions have occurred for a user, after a minute or so, it's supposed to start going down by itself. And that result is supposed to be written to the table and update what's already there. This table is being used by a machine learning algorithm that is going and checking to see when it receives a transaction, how many transactions have occurred over the last 5 minutes for that user. And delay. There we go. So at first you're like, oh, calculating a count over the past 5 minutes. That sounds simple, right? And then you start to think about it. You're like, well, I need windows, so maybe a 5-minute window, but wait a minute. Fixed windows are fixed. You set a window from 11 to 11:05. Well, what if you receive a transaction at 11:03? You're going to need to compute a count across windows. So fixed windows isn't going to work. You want about sliding windows? Well, then your record could land in multiple windows, but you still can't guarantee everything's going to fit within those boundaries. That's not going to work either. Now, Spark Structured Streaming has something called session windows. But again, session windows arbitrarily grow, but it will grow until no more records are received and then emit an output. So that's not going to work either. So actually, how the heck do you calculate from the last 5 minutes from right now? How do you do that? And that is where flatMapGroupsWithState and applying pandas with state comes in. So this is the example that I'm going to show you as we step through the presentation. Now, how do we think about this logic? Often when people are looking at flatMapGroupsWithState or applying pandas with state, they're thinking they're receiving the entire microbatch into the function. Well, that's not true. So take a look at this here. We have 6 records in this microbatch. Now, obviously, I've simplified it dramatically. You usually have far more. But I've got 6 records in this microbatch. I've got 1 for user ID 1, 2 records for user IDs 2 and 3, and a record for user ID 4. flatMapGroupsWithState is going to be called 4 times, once for each user ID, once for each key. Within flatMapGroupsWithState, you are not going to have the records for multiple keys within it. You're going to have all of the records for 1 key in it. And that is how you need to define your logic. You're not defining logic to compute across keys in flatMapGroupsWithState and applying pandas with state. So right away, that does simplify the way you need to think about it. You've just got 1 key in hand and its records. Do your computation. So this is how to break down the logic for arbitrary stateful operations. There are 4 categories that you need to consider, and that is regardless of what use case you are implementing. And we're going to go through each of these and have example code of each. We need to define our data structures. We need to define some initialization logic. You need to define your steady state logic. And then, optionally, you need to define timeout logic. So let's go through each of these. First, you need to define your structures. What I mean by your structures is you need to know the form of the data that's coming in, the form of the data you're going to save in state, the data you're saving in between microbatches, and then the form of the data that you're going to emit. Now, these 3 structures actually don't need to look anything alike. They can look completely different. It is up to you. So let's start with the Scala example, since that's the one that's been around for longer. You are going to need a definition for in, state, and out. For Scala, this is commonly done with case classes, although tuples work as well. So in my example, the data that I'm receiving in, just to keep it simple, is a user ID and a transaction timestamp. For state, just to make my logic easier when we're defining the steady state logic later, I'm keeping 2 columns. I'm keeping the latest timestamp, and then I'm also keeping a list of the current purchases, which is a list of the transaction timestamps. And that's what I'm going to keep in state in between each microbatch execution. It's going to make math easier for me. And then when I am spitting out, you'll notice that it looks different than the input and the state. I'm going to output the user ID. I'm also going to output the count, which is the count from the last 5 minutes. And then for my own visibility and debugging, I've also added a couple of more things. I wanted to output the event timestamp that I just calculated the count for, and an is timeout. And when we talk about timeouts, you'll understand why, for my visibility, I was curious to test that. This is going to tell me whether the calculation was because I received records or because I didn't receive records. Really? Wow. Yep, hold on. Our IT department sent out something yesterday saying they had to update all of our laptops starting today. So of course, they waited till right now to send it to my computer. Moving on. So once you've defined your 3 structures that you need, there's a little more structure you need to define. You need to define a function with a specific set of parameters that the flatMapGroupsWithState function is going to call. You can really name it whatever you want. I just named it updateState. The first thing you need to define is your grouping key. What key is coming in, and you need to give it the data type. You can name that field whatever you like. I named it user ID because that is my key, and then I know it is of a type long. The second parameter is going to be an iterator containing all of the records for that key that have come in. And the third, I need to define the structure of the state that I'm going to store and pass it in. So here you see I've passed my case class for the state. Then finally, I need to output an iterator. That is what's going to be output from this function of type purchase count, which is the case class I defined for my output. In the body of the function, there's also a couple more structures that you need the majority of the time. First, you need to define a structure to store the output records, and then set it to the case class for your output type. This depends on your logic. If you're going to go through some complex logic and just be adding records over time, you want to define a structure at the beginning that you've got ready to go to just add it to. Now, this is important. If you're going to access your input records more than once, so look back at the input records, the values field. That is an iterator. Iterators are one-pass data structures. Once you've gone through them once, it's gone. So if there's any chance that in your business logic you need to access these input rows more than once, you're going to want to put them in another structure so you can access them over and over. So that's what I've done here. Finally, to be returned, it requires an iterator. That iterator must be returned even if it is empty. So in this example here, make the conversion of the iterator the last thing that you do. Now there's a reason for that. This is Scala specific. You cannot use a return statement in Scala in this case. Returns in Scala work differently than in Python and Java. So if you use a return statement, you can actually end up with an empty iterator, which is not what you want most of the time. So when you're doing this in Scala, make sure to convert your structure that you defined for your output to an iterator as the last step, because Scala will return whatever was last. Now let's talk about Python. And I was very happy to get the Python API for this, by the way, because it's unlocking several customers that are Python shops. This is going to look similar, but there are a few differences. Definitions are required for what the state's going to look like and what the output records are going to look like. They must be either DDL strings or struct types. The reason for this specificity is that they are going to be passed to the apply in pandas with state call. These are two required arguments. So it's good to define them at the beginning. In my example, I also still wanted to have a comment with my input type just to remind me while I was going through my code. That's obviously not required. I'm just addicted to comments, so I put it there. And then in the middle of my code for this, I am passing around a state object multiple times. I don't want to have to reference that object by number. You know, in Scala, I had the case class. You don't have a case class exactly in Python. So I used a name tuple, just so I can reference those names in my code. Not required, but this is a structure that made it simpler when I was implementing. Now this is going to look familiar, just slightly different for Python. You do still have to have that function. Your first variable in the function is going to be the key, but the type is different. The key in Python is always passed as a tuple. It's passed as a tuple of NumPy data types. Even if there's only one key, because you can have one or more fields in your grouping key, but even if it's one key, it's still going to be a tuple. You do need to give it a data type for that tuple. And now here in Python 3, you'll notice in Scala, my example had that as a long. Python 3 actually doesn't have a long data type anymore. So the long type in PySpark matches to an int. That's why I need to define int there. And then that second parameter, the type looks a little different than it did in Scala. It's going to be an iterator of pandas data frame. The third parameter is, of course, the group state. And in true Python fashion, we're not providing a type there. It is passed into the function, however. And then we are returning an iterator of pandas data frame. Just like in Scala, you can pass out 0, 1, or more rows with each execution. Now remember, this input is still a one-pass iterator. So I've got code in here to go and move that to another structure, since I needed to access that input more than one time. Now, if you're looking at the specific code, really all I needed for my logic is that list of transaction date times, so that's all I pulled into another structure. And that didn't go. There we go. In order to return that iterator of pandas data frame, I'm using a yield statement here. That yield is going to return a generator object. It's going to be converted to a PySpark data frame automatically, so when you use the value that's passed out of applying pandas with state, it's already a PySpark data frame. You'll see the fields are the same fields that I used in Scala, except I added an additional one, because for my example, I wanted to also see what transaction timestamps I had in state. So I actually also have code that pulls those transaction timestamps out and just sticks them in a string, and I used it as part of my return type, so I could validate my math. Now that we've defined our structures, the next thing we need to do is define our initialization logic. Now, what do I mean by that? Well, as we're going along, we are going to receive user IDs that we've never received before. There's no state for it yet. So what do you do first? This is your initialization logic. In Scala, there is a state function called getOption, getOrElse. Now, for Scala folks, this will be familiar to you. If the state exists, it will return it. If the state does not exist, it will execute code that you've provided to initialize it. And now here, all I needed to do is just grab any transaction timestamp and then go and have an empty list of input row. How is it different than Python? Well, I don't have that get or else in Python. So I defined an initial value, and then I checked if the state existed. And if the state existed, I replaced my initialization value with the actual state. It just reversed the order, but it's the same thing. So the initialization is usually the simple part. Now we're coming to the meat of what we are implementing, which is the steady state logic. What do you do when you get new records for a key? This is where most of your logic is going to come from. And this is often where the complexity that you need can be provided. So the first thing I recommend is writing supporting functions. Keep the function that flatMapGroupsWithState or implying pandas with state is going to call simple, and write supporting functions. These supporting functions can also enable some unit testing, so you could make sure your logic is working properly before you put it all together. In my example here, my logic is actually pretty simple. I need to add new records to the state. I need to remove expired records from the state. In our use case, we only wanted to do a count for the last 5 minutes. So if we have records in state that are older than that, we don't need them anymore. And we can expire them and remove them before we do the count. Then we generate output records. Now, since my logic was very simple, I did not provide a separate function to just do a count. But I'm providing an output record here, and then I'm adding it to my structure that I was going to convert to an iterator at the end. Finally, I'm updating the state object. Now, this is important. This call is what is going to end up saving my altered state back over to the system, so it persists between microbatches. You only want to do this once. This is an expensive operation, so do not start up a loop and end up iterating the state over and over. You won't like your performance results. But if you do this once, then you're just going to save state once. Now, how about Python? Python, again, looks very similar, just different syntax. I'm adding records, and I'm removing expired records, just like before. I'm then updating the state object. Since I don't need to adjust the state anymore, it doesn't really matter where in my logic I adjust it, as long as I only do it once. And then finally, I'm calculating the output and returning a yield statement. Now, there's a couple of things that are a little interesting here. Notice how I'm accessing the value of the user ID in order to return it. So this is a funny quirk with Python tuples. If you've only got one item in the tuple, you have to have that hanging comma. Otherwise, you're going to get the object instead of the value of that key. So thought I'd throw that in there because people will run into that. And then here, since I already have a list of transactions, I'm just doing the len function, and I'm getting the count. It's pretty simple. Whoops, that jumped. And then finally, at the end, you're seeing that yield statement where I'm building the data frame, the pandas data frame, and then returning it. Now let's talk about timeouts. What are timeouts? If your logic needs to do something when no records have been received for a key, then you need a timeout. Timeouts are optional, but they can often be very useful, especially if you don't receive records for a long time and you don't want to keep taking up state for that key. Do you need a timeout? Well, if results need to be output when no records have been received, then you definitely need a timeout. In our use case, we're supposed to have the count in the destination table go down over time if we don't receive records. So we definitely need a timeout. Timeouts are going to fire when no records have been received after a configured period of time for a key. This is still on a key-by-key basis. So if this is the only key that hasn't received records, its timeout will fire. Whereas with other keys, the steady-state logic will fire when they receive records. You can configure these timeouts based on event date times in your data, or you can use wall clock time. Both are fine. If you're using the event time, you are required to specify a watermark when you're calling the arbitrary stateful operation. And then these timeouts are not going to be precise. So we're not going to look for absolute precision here. This is something that will come close to what you specify, but won't be exact. They can be delayed, depending on how long a microbatch takes to execute. If you say timeout after 1 minute, but your microbatches are taking 2 minutes to execute, the following timeout is going to get delayed. And then here is the biggest thing. If the stream is not processing any data, nothing is going through it for any keys, then timeouts will not fire. So if you have logic that really depends on timeouts, but there may be times when no data is going through your stream, it'd be a good idea to send, just a little no-op message through there, just so all of your timeouts will fire. So let's look at our use case. It's fairly simple. First, you're just going to add a conditional. Add that conditional around your steady state logic, and just use the state has timeout method to determine if this call of flatMapGroupsWithState was due to a timeout or not. If it was not due to a timeout, then you're going to execute your steady state logic. And then if it was due to a timeout, you're going to execute the logic that's defined in the else. This is how to specify a timeout. Now in this case, I am using an event timestamp that I just pulled from my existing data. And then I'm saying 30 seconds after this event timestamp. So when I see data come through that is 30 seconds later, it's been 30 seconds. Or if I'm counting, it's going to go through and wait for 30 seconds plus the time of the watermark because I'm using event timestamps. That's why you have to specify a watermark. So in my example, this is going to happen in about 1 minute because I'm specifying a watermark of 30 seconds, and I'm saying I want my timestamp to be 30 seconds. Also, whenever you execute this function, the timeout is going to be cleared. This is why you need to specify it every single time. You do not need to say if timestamp exists. You won't find that anywhere in the code. Instead, you're just going to specify it at the end of your steady state logic, and you'll specify it again at the end of your timestamp logic if you want it to keep firing. Now this is our timeout logic. When a timeout has fired, that means that there are no incoming records for that key. That iterator will be empty. So you don't need to worry about them. You also know that there is state present. If there was no state present, you wouldn't have been able to execute this code in the first place, because this would be the first time you've seen the record, which means you would have received a record. So when the timeout fires, you know you've got state present. In our use case here, I don't need to add new records because they don't exist. So instead, I'm just removing records, and then I'm redoing the count and outputting it. And finally, I am re-specifying the timestamp. In this case, I just added to the clock time to come up with some sort of time, and then added 30 seconds to it. Now, how is this different in Python? Not very at all. It's the same logic, just different syntax. Again, you're going to have your conditional, and again, you're going to specify that timeout. There is one difference here, where a millisecond value does need to be provided to the set timeout timestamp function in Python. So that's why you see me calculating a millisecond value there. So the logic is really the same as Scala, and just different syntax. You see us getting the state. You see us removing those expired records. You see us setting the timeout. You're seeing us calculate the count again. And finally, you see us returning with that yield statement. Those were all of the components. That was it. Once you know how to think about each one of those components for arbitrary stateful operations, then you can implement your use case with it. And the only complexity will be whatever you need in your business logic to execute that really complex business requirement that somebody just handed you. So let's go through this design summary template, first Scala, then Python. I've highlighted here. These are the sections where you're defining your data structures, what goes in, what is saved, and what comes out, the definition of the function, and supporting structures that you need internally to do your logic and to output. Here we go. You're going to define your initialization logic here. Then you're going to define steady state logic. And you're really going to use helper functions as much as possible to facilitate that unit testing and to keep this function that you're calling from flatMapGroupsWithState very clean. And then finally, if needed, you're going to have timeout logic. You're going to have that conditional, and then you're going to implement your timeout logic below. Now, I wonder if anybody spotted it. I actually implemented my timeout logic kind of inefficiently. Can anybody think of why? I wonder if anyone thought of that. Yeah. What was inefficient about my timeout logic? Even if I've gone to 0, yes. What would be better? Because so I don't know if everybody heard what he just said. Yes, even if I've gone down to 0 transactions, I'm still maintaining a little bit of state for that key. If that user ends up sending no more transactions for the next 3 weeks, I'm still checking every minute to see if they've sent a transaction in my timeout logic. That is very inefficient. It is perfectly valid to, when you come down to 0, go, you know what? I'm checking state completely, and I'm not resetting a timeout. Then nothing will happen again until that user actually sends a record, and we can start all of this logic again. Now, Python, pretty much the same thing, just different syntax. I love it how everybody's phone comes up for Python. See, this is why I love that we have implemented the Python API. We are doing the same thing. We're implementing our structures, including my silly comment, but I really am addicted to comments, and so I wanted to remind myself what my input was. We've also got the definition of the function. We've also got internal structures, and finally, defining the output. And then we have our initialization logic, same thing, very basic in this case. The meat of our logic, these are our functions that are adding to state. removing from state, calculating, and returning. And finally, our timeout logic, that conditional, setting the timeout, and then executing timeout logic there. How the heck do you call this thing? Well, yeah, let's go over that real quick. So for Scala, this was just convenient for me. I already defined a case class saying what my input row looked like, so I'm just going to convert it to that case class right off the bat so I can pass it in without any whining. And then this is how you call flatMapGroupsWithState. Let's go through the pieces really quick. So here, because I'm using an event time that is in the data itself, I was required to specify a watermark, and I just specified 30 seconds here. This is my grouping key. I'm grouping on the user ID. This is my output mode. In this case, I'm using append, but update mode is also allowed. I don't know if you guys are familiar with Spark Structured Streaming's output modes. It's append, update, and complete. These functions support both append and update mode. This is where I specify the type of timeout that I'm using. If you don't want a timeout, that's no problem. You're going to specify no timeout in this argument. And this is the function that I'm calling. What's going to be returned in the Scala use case is a data set with the type of the case class. You can pass that data set on or convert it to a data frame, do whatever you like. Just keep in mind that a data set is what's being returned here. Python, a little bit different. We're still defining that watermark because it's event time. And I'll let people take pictures. The group by key looks a little different because we do need to specify a tuple. And both in Scala and Python, you can have more than one grouping key. This is the function we're calling. This is the interesting part. It is different than the flatMapGroupsWithState implementation. You are required to pass the output schema and state schema to the function itself. That's why there was the requirement at the beginning for how you define those structures. Again, we're using append mode. And again, we're specifying the event time timeout. What's going to be returned from applying pandas with state is a PySpark data frame. So it's already in data frame for you. So after that, you just treat it like you do any other data frame. What the? My clicker is really hyper. What about syncs? What about them? Nothing different. Use your favorite sync. It does not matter. The one quirk that I found people run into is if you're using Scala and you've got a data set come back, and then you try and go into for each batch. Make sure to define that you're passing a data set in there instead of a data frame. I recommend converting it to a data frame. One other interesting thing here is that you know how it's important how windowed functions, they will emit data differently based on whether you've specified append mode or update mode. You'd think that maybe something in here would be enforcing that type of behavior. It is not. You put that append in there, it's just like you wrote the word append. It's really not enforcing anything on the system. The system is assuming that you are enforcing those semantics. So since we're already doing something complex where we need to go outside the box, cheat, nothing is going to care. So you can actually have it emit whenever you want, whatever you want, regardless of the output mode that you put in. Streaming best practices. So remember, this is stateful streaming. If you have millions of keys, you will want that RocksDB. Or you will have much sadness, and there's nothing we can do about that. Use RocksDB for that. In addition, if you're using Databricks, we have a few goodies in there too. We have asynchronous checkpointing, which reduces the latency for stateful streaming dramatically since we are separating out the checkpointing from the actual processing. We also have state rebalancing. So if you have a cluster that may lose nodes or add nodes, you want the state to be redistributed across them. So we have state rebalancing for you now, which will help with performance. And then you can also set an initial state. If you want to start over from a new checkpoint, you may not have to start over from scratch. So in Databricks, you're able to specify an initial state for these functions as well. There we go. All right. Last slide, and then I'll open it up for a few questions. A few things to keep in mind. You always read the fine print no matter what you're doing as software engineers, myself included. Only update the state once during each execution. It is an expensive operation. I can't emphasize this enough. If record order matters in your logic, there is nothing that is enforcing it. So you need to enforce it. Within your arbitrary stateful operation logic, if order matters, make sure to sort. Also keep in mind that you can receive records out of order across microbatches and plan accordingly. Remember, you're keeping what you want in state. So you can keep as much as you want ordered before it doesn't matter anymore, but take it into account. Another one that does trip people up is when the stream is not processing any data, timeouts won't fire. So if something's critical there, remember to just shoot it a no-op once in a while so all your timeouts fire. And then a strange quirk I encountered for Scala only when I was working with a notebook. Those 3 case classes, they have to be defined in the same function that a flatMapGroupsWithState is going to call. Otherwise, that function can't find them. I don't know why. I haven't bothered to look. But that was it. Now let's see who was paying attention. What are the 4 categories that you need to take into account when you are designing logic for arbitrary stateful operations? The first one is defining data structures, yes. The second one, you have to define logic for initialization. The third is your steady state logic. There's one side of the room that's awake. And the fourth one is optional. It's timeouts. There we go. Everyone else woke up. So that was all I had. And actually, we've got like 3 minutes for questions if anyone wanted to have me answer something on stage. And then I am available afterwards to answer questions for you as well.